Hello and welcome to webinar on holistic engineering design. As an intervention, I feel extremely proud to be inviting you all to this webinar. In fact, this webinar is being broadcast under the social corporate responsibility of Innovate in order to do a bit to the society, especially in the COVID times. And Innovate profusely thanks all the participants for your kind attendance. Thank you for sparing 2 hours for us. And even if you pick one leaf from the webinar, we'll be extremely delighted and we'll be extremely grateful to you. Now, given the population and the composition of the participants, we may not be able to take questions and queries during the live webinar, and therefore these are the email IDs that you can see on the screen, to which you can write your queries and questions, such that all the queries and questions will be answered within a stipulated time and would be posted on our website, so that you can have a detailed look and even you can download that. And as far as the presentation material for this webinar is concerned, it is also going to be available on our LMS, which you could view. May not be able to download because it might have some copyrighted information. So let's get started with the webinar. In fact, the webinar would have 2 sections. The first one would focus on the technical challenges for a designer given the current engineering trends. And as far as the second section is concerned, it would focus on the expectations of the industry from an aspiring designer or an analyst. And during the discussion, we would also look at several obvious facets of the design, and also would emphasize the need for engineering hand calculations even in the era of simulation. So let's get started. Now, before we look at the competency wheel, which we have conceived after a lot of research and consulting several competency heads across the OEMs and research labs. In fact, the difference between analyst and a designer is not significant if you are looking at design changes or design improvisations. But if you are looking at a situation such as new product introduction, the difference becomes significant. Because if you look at a basic list, in fact, a designer incepts by establishing the design envelope. And what exactly I mean by design envelope, it is the space occupied by your component during the worst operating condition. That means your neighbors may be growing thermally, they may be getting deflected mechanically, and they may be eating into your space, but you got to have no physical interaction with the surrounding components, and also maintain adequate clearances, which are very, very important from performance perspective. And once you have the design space established, it is followed by concept sketching, and the concept must be evaluated for various risks. It need not just be strength failures. It can be a buildability issue, it can be a manufacturing issue, it can be a performance issue. So there can be several issues that have to be looked at before you select the best concept. And further, you may also have to worry about instrumentation, testing, measurements, and finally you may have to worry about standardization. Of course, in case of simpler components, the standardization could happen without test, and in many cases, standardization may require a very, very detailed testing. And if the material that is being used is new, then you may also have to do a detailed material testing also. So now all these facets are going to be discussed during the webinar through various situations. We are just making a mention of it at the beginning so that you could have an expectation of the nature of discussion to follow. And now let's move on. Yeah, this is Now this is the typical engineering wheel of competencies for a typical designer, and several of these competencies are also needed for a young analyst. Now the first one being the product familiarity. The product familiarity is a very important aspect, and here we'll be emphasizing on two areas, that is system understanding and then the component which are very important for a young designer. We'll be talking about it in detail as the discussion progresses. And as far as the material selection challenges go, today most of the industries are resorting to probabilistic methods, and as an example we would be looking at probabilistic characterization of materials. We would cite an example and discuss in brief, given the time constraint, the idea of probabilistic fracture mechanics. And also a designer must be familiar with various methods and should have a detailed understanding about stress and vibration margins for a component, because these are very fundamental for component design. And today NVH also becomes a very important characteristic to be addressed. For example, for an electric vehicle, the other noise sources are rather can be neglected, but road tire interaction might become a very significant source of noise. And also engineering standards and design standards are very important, and you've got to be familiar with it. And optimization is something that is inevitable in current engineering situation, and sensitivity analysis is very important. To give you or to impress you upon the need for sensitivity analysis, a very simple example is, let's say you're trying to life a component, and whatever assuming that it is stress based, if you are making an error of 5 to 10% in the stress computation, then the predicted fatigue life can vary by 30 to 40%, and that is what we call sensitivity. That is, any structural response may be influenced by several parameters, and the parameter that influences the structural response to the maximum is the parameter of interest. And then today you are talking about several active systems. That means we are talking about controllability and observability, and obviously you're talking about sensors and actuators. In fact, in the discussion that we get is the arrest mark, which may not be present in the LCF. So these are some of the important aspects that a designer, especially a young designer, must be familiar with. So let's move on, and now let's look at the system design. Now here I have chosen a very interesting example, that is of bearing support structure. You can see that in the figure there is a shaft, and there is a bearing, and you have the bearing support structure. You can see in this particular figure, it details you have the bearing housing, and then you have the bearing support structure, the bearing itself. Now what we have essentially done is we have clubbed the stiffness of the bearing support structure and the bearing housing, and then represented that by an equivalent spring. Now why do I say that one component could have multiple roles? And that is where the system understanding becomes very important. Now you can see that one of the things that this support structure would do is reduce the stiffness of the system. Once it reduces the stiffness of the system, in fact the natural frequency of the system obviously goes down. That is, if the natural frequency goes down, the critical speed margin does get affected, because the natural frequency is generally kept above the operating speed, and once you have the natural frequency brought down, obviously the critical speed margins are compromised. Secondly, this is the only structure we would explain in detail. This is the only structure that would provide the damping, especially in a gas turbine situation, because the whirling shaft may not undergo strain alternation, because for any hysteretic damping to be produced, there must be a strain alternation which cannot happen in the shaft, and that comes from the static support structure. And also importantly, you can see the tip clearance. Be it compressor, be it turbine, the tip clearance is of utmost importance, and therefore it has to be maintained, and a stiffer bearing support structure would mean the tip clearance is maintained. Now let's understand these facts in detail. Now look at the figure. Now it is very easy to understand. If I keep the shaft on a rigid platform and try and deflecting it, then it would deflect by a small amount, that is to the extent the shaft is flexible. But if I keep on a flexible platform as shown here, you can see that the deflection increases significantly. That means the bearing support structure brings down the overall stiffness of the system. And if you observe carefully, in fact, the stiffness of the bearing support structure is in series with the stiffness of the shaft, and therefore the overall stiffness is brought down because both are in series. And you can see for the typical figure shown, this is the natural frequency, and if I remove the bearing support structure stiffness, the natural frequency obviously goes up. Now especially in gas turbine systems, unless in the automotive systems where you can have viscous damping in the form of shock absorbers, you cannot have that in gas turbine situations. There the dependency is mainly on hysteretic damping, and a whirling shaft, if you show a little consideration, would not bring about any hysteretic damping because it does not suffer strain alternation. What the bearing support structure does as the shaft is whirling, and as a consequence what happens is it provides a hysteretic damping of almost 4% of the critical damping, which is very, very significant. And since it also comes in the path of the gas flow, the bearing support structure has to be designed as slim as possible, because otherwise it would be obscuring the gas flow. If you assume that the gas is flowing in this region between the bearing support structure, the bearing support structure must be made as lean as possible. So now coming to the third point, what happens if the tip clearance is not maintained? Please remember that if the tip clearance of a compressor is increased by 1%, what exactly I mean by tip clearance? It is nothing but the radial distance between the casing and the blade tip. This is the tip clearance. If this is brought down by 1%, of course the performance may go down by 1 or 2%. That is the efficiency of the compressor, but the surge margin gets significantly compromised. So therefore, it is the stiffness of the bearing support structure that has got multiple roles. It is not that it just controls the natural frequency. It provides the hysteretic damping. It also controls the tip clearance. Now let's dig deeper. This was the basic understanding. Now, the bearing support structures can be inclined struts. That means they also would have axial stiffness. Now, the radial stiffness is used to maintain the clearance, is to ensure the rotor dynamics of the shaft, and the axial stiffness is used to support the thrust loads. Because if you look at a typical compressor and a turbine setup, in fact the pressure is increasing across the compressor, and the pressure is decreasing across the turbine, and as a consequence the thrust load on the turbine is in the rearward direction, and the thrust load on the compressor is in the forward direction, and as a consequence, what happens, there is a net thrust load which has to be supported. Now, why it becomes very, very challenging as we try and understanding the system to a greater extent. Now let's say that we are going to make the support structure stiffness very, very high. That means we are designing the support structure to be very, very stiff. What happens, let's say if the shaft is subjected to unbalance, all the load is actually transmitted from the shaft to the casing, right? As a consequence, the whole engine vibration can get affected. But if we design the bearing support structure stiffness to be lower, then what could happen is the shaft rotor dynamics gets affected. That is, you are compromising with the vibration margin, and also your tip clearances can get affected. So it is the trade between rotor dynamics, tip clearance, and also whole engine vibrations that has to be carried out, and that is what the challenge for an young designer, because he has to understand several facets that are directly or indirectly linked with his or her component. It is not just the one component alone. Now, what becomes very, very challenging as we proceed further? Now, if you look at a typical gas turbine, there can be a lot of maneuvers, but of course for a civil aircraft, the maneuvers are quite disciplined, and it is far less compared to your military aircraft. But whenever a maneuver happens, it brings about very, very important loads, inertial loads and gyroscopic loads. Now look at a typical situation. Now when the aircraft is moving absolutely steady, there is no gyroscopic load. Look at this rotor. Let us say it has a certain angular momentum I omega, and once the aircraft does yawing or pitching, that is, you can say this is the aircraft axis. It can actually roll, it can actually pitch, and about the vertical axis it can actually yaw. So this is the yaw axis, this is the pitch axis, and whenever the aircraft yaws or pitches, this angular momentum of the rotor does change direction, and as a consequence you have gyrocouple. You can see that the gyrocouple is in fact go to increase the bearing reactions. If these bearing supports were not rigid, then that would cause a significant deflection of the shaft, and therefore maintaining tip clearances during maneuvers becomes very, very challenging. In fact, if you look at the data, the military aircrafts have almost 3 times the precession rate that of the civil aircraft, and in fact if you have a precession rate of 3 radians per second, then you would have bearing reactions which are almost 12 to 15 times. That's a mind-boggling number compared to the normal operating load. And this is the effective gyrocouple that you can calculate. This is because both yawing and pitching are about 2 perpendicular axes, and the resultant can be had like this. So it is not just the design considerations have to be at the operating point, but during extreme maneuvering situations, the design assumes a greater complexity and becomes much more involved and challenging. So that was just the tip of the iceberg. We haven't discussed the mechanical fuses for bearing support structure, because I said all the loads from the shaft is transmitted to the casing via bearing support structure. If there is an extraordinary event, that is like the blade release, either the fan blade release or the core blade release, the bearing support structure can get damaged, or if it is strong enough, it can damage the rest of the engine. So therefore mechanical fuses have to be provided. We haven't discussed the asymmetry of the support structure. They may also have to accommodate the fluid pipes. They are also responsible for keeping the casing perfectly round. We haven't discussed about the differential thermal growth. If at all the bearing support structure fails, what happens next? There can be a lot of issues that one has to address. So the message I am trying to drive home is that the system understanding for a component designer is very, very important, because if your component underperforms, there can be cascading effects across the system. So now let's move on. Let's take a simple rotating bolted joint. Now, here I am talking about an unobvious failure mode. Now, what is the basic design intent for designing a bolted joint? It is the axial restraint, right? It is the axial restraint for which the bolted joint is designed. Now, when the bolted joint is subjected to a large angular velocity, does the effective clamping load come down because of that? And that is the question that we need to answer. Now look at this particular simple plate that is being rotated. And if that is stretched because of the centrifugal loading, obviously it suffers a lateral contraction. That is, it gets compressed laterally. That is because of the Poisson effect. And the same thing can happen to the flanges also. When they are subjected to centrifugal pulling, what exactly happens is that they suffer a lateral contraction as shown here. And as a consequence, the pressure between the flange and the nut, the pressure between the bolt head and the flange goes down, and that in fact brings down the clamping load. You can see this expression. Here we have considered mean hoop stress and mean radial stress for these two flanges, and then the Poisson's ratio. When the stress is divided by Young's modulus, we in fact get the strain multiplied by the Poisson's ratio, and then the thickness of the two flanges would give us the axial compression or the lateral contraction, and that multiplied by the effective stiffness. When I say effective stiffness, both the flanges and the bolt are in series, and that is KB represents the stiffness of the bolt, KF represents the stiffness of the flange, and multiplied in the effective stiffness by the axial contraction, we in fact get the loss of clamping load. So sometimes a designer has to observe very, very carefully. The reckonings may not be simple. Just to impress upon you, a bolted joint could have so many possible failures. In the webinars to come, we can have devoted discussions for all these. But now, one simple question for those students who are watching this webinar: what exactly happens if I include a bracket in a bolted joint? Remember, the stiffness of the bracket is much smaller compared to the stiffness of the flanges. That is the hint for your question. Now try and post your answer at our website, the addresses which I mentioned at the beginning of the webinar, and those who get the correct answers will be awarded with some prizes. Of course, there will be a lot of questions as we progress, so let's move on. Now let's look at one important trait for designers, which is called pattern recognition. What exactly I mean by pattern recognition? Pattern recognition essentially means that if I confront a phenomenon in one product, the same phenomenon may repeat itself under some other condition in some other product line. So one concept that I have taken is discontinuity. Whenever there is a change in the material or change in the mechanical deflections, the discontinuity could come about. Here I have chosen three situations. One is that of a composite beam. The second is that of a pressure vessel. Third is that of a disc and a drive arm. Now, the first situation is obvious, aluminum and steel, since because of the change in the material, there can be discontinuity at the plane where these beams are joined. The second needs a little bit of thinking, because if you look at the table, you can easily figure out that the cylindrical pressure vessel is growing more than the spherical pressure vessel does. And as a consequence, at the interface where these two are joined, there is a local bending, because this cylindrical pressure vessel wants to grow more, but the spherical pressure vessel is not allowing it to. So this is restraining this, and a local bending is caused. And what is happening in this particular situation, you can see the disc wants to grow more, but the drive arm may not be. So if you attach at certain radius which is not well determined, either the drive arm can restrain the disc growth, or disc can restrain the growth of the drive arm. Here we are assuming that the disc is subjected to only centrifugal loading. That is, it is subjected to a large RPM. So the disc is growing, and the drive arm is also growing, and the drive arm is attached to a shaft for transmitting power. Here it is not just the mechanical loading. That is, I spoke about centrifugal loading for the disc and drive arm. I spoke about pressure loading. Here maybe the bending loading, but it can be the temperature also, because if the two components do not have the same thermal coefficient of expansion, even the thermal mismatch can arise. So that is also very important. Now if you look at carefully, there is a resultant bending that is taking place at the interface, and because of which there is a stress that is developed. This stress may not cause a burst or anything. It is also called secondary stress. It is a local stress. But what is important is this stress rise at this particular point, that is at the junction, would not die in a small distance. If the stress raises, it will take certain distance for the stress to attenuate. That is, it rises at this juncture and it would attenuate over certain distance. And if you have any feature, let's say a hole in that particular region where the stress has not still attenuated, has not died out, then that feature can become distorted. And if that feature is used for any design purpose, then the performance can get affected. That is very, very important. So let's move on. Now I was talking about the disc and the drive arm. Now the question is, where exactly you must attach the drive arm so that they do not restrain each other. In fact, if you look at here, the drive arm should be attached at certain radius, such that neither the drive arm restrains the disc nor the disc restrains the drive arm. And how do you determine that? A very, very simple concept is adopted here. You imagine that that radius is expanding freely like a hoop. When I talk about a hoop, it is just a thin ring which is subjected to centrifugal loading. If the disc has the same growth at a given radius as does a thin hoop which is subjected to angular velocity about its own axis, then at that radius, if you attach the drive arm, which is also called free hoop radius, would not feel restrained at all. So the point I am trying to drive home is it can be stress stiffening, it can be discontinuity stresses. These phenomena repeat at several instances across several product lines. So a young designer or an analyst must be very, very careful and sensitive to these issues. This webinar, you may not be able to learn much mathematically, or ability to quantify you may not develop. But if you develop sensitivity to these issues, I think I would be more than happy. So now let's move on. Now, how do you in fact deal with transient temperature gradients? Here is one more example of a typical turbine disk. You can see that the bore actually has much higher thermal mass and therefore has a large thermal inertia. That means you require huge amount of heat to be given for this to get heated up. And as far as the rim is concerned, it has low thermal inertia, it is obvious, and these are joined by a diaphragm or a web. Now, one of the challenges that you would have is when you start the gas turbine, that is, in the initial few minutes, you will have a temperature gradient which is significantly large. That means the rim has the highest temperature and the bore has a relatively very low temperature, and this thermal gradient can be very detrimental. Of course, whatever the thermal gradient I have sketched here is ideal steady state. In fact, it is determined by the material. For your information, if it depends on whether we are using titanium or Inconel, either it can be a fourth power of the radius, or it can be a second power of the radius. That is, it varies as r power 4 or it varies as r power 2. So therefore, that is very important. Now, when the transient conditions exist, that is, when the rim is hottest and the bore is relatively cooler, rim wants to grow, but it is restrained because of the heavy bore. And as a consequence, you actually have plastic compressive stresses in the bore, rather in the rim. And when you cool it down to room temperature, because it was shortened in the transient phase, it develops residual tensile stresses. So this becomes a cyclic phenomenon, and this may lead to even rim cracking. That's very important to note. And as a consequence, you will have to deal with transient thermal gradient, because evidences have shown if you deal with it successfully, then the fatigue life of the disc can be improved almost 3 times. So that's a very mind-boggling number, but indeed it is true. Now, what are the best practices? See, one thing you'll have to understand that in the steady state, this thermal gradient is designed because the bore has to remain cooler because it has to support huge amount of centrifugal loading. Even from your basic BTech curriculum, you would have appreciated that for a disc with a hole, when it is subjected to centrifugal loading, it is the bore which has the highest hoop stress, right? So therefore, it has to be kept cooler. And also, please do not forget that it is closer to the bearings. So therefore, rim cannot become very hot, but this transient temperature has to be dealt with. How do you do? In some of the gas turbine technologies, what they use is they devote some of the combustion air to heat the component so that it is hurried to the steady state situation. That's one of the technologies that is adopted. And also, what you can do is you can make the web or the rim which is connecting the cold and the hot ends as thin as possible. What happens because of this? This in fact does not restrain the rim from expanding. If you make this leanest possible, then what happens is this can be applied to any general situation, not just to the disc. Then what happens is it allows the rim to expand to a certain extent, the constraint is released to a certain extent, and the thermal stresses are indeed reduced. But of course, you will have to ensure that the stress margin and the elastic buckling margin of this are indeed ensured in the process, because design, as I have been emphasizing, is always a trade. If you are trying to satisfy one constraint, the other constraint pops up, and if you are trying to satisfy that constraint, you are compromising with this. So it is design is always a constrained affair, so therefore we'll have to be careful. Now let's move on. Now why, if you read any of the statutory documents for a gas turbine, what is very important is the integrity of the shafts. Why? Because any shaft failure can bring about catastrophic failures. Now, let's consider a simple situation of a compressor joined to a turbine. Now, what happens if the shaft that is connecting the compressor and the turbine is broken or it fails because of some reason. Then please understand, to begin with, in a typical gas turbine, all the work developed by the turbine is completely consumed by the compressor, because the compressor is the power absorbing machine and the turbine is power generating machine. Now, if the compressor is disconnected from the turbine, all the inertia that is being driven by the turbine is cut off. That is, now it has very, very low inertia. It has the inertia of itself, because the compressor is cut off, and therefore it starts speeding up. Incidentally, let me also mention a fact that a single stage of a turbine is able to drive several stages of compressor, and that is because the compressor has adverse pressure gradient. That is, it cannot absorb more power in a given stage. Therefore, several stages of compressor is driven by single stage of turbine. Now, once the compressor is cut off, what happens? The effective inertia is significantly reduced, and within a few seconds, in some cases it is in less than 1 or 2 seconds, the turbine starts overspeeding, and that can lead to what is known as disk burst. How do you avert such a situation in a real time? As a designer, if you think, one of the solutions could be close the fuel valve, because you stop supplying fuel so that the speed is reduced. You can also open the bleed valve so that the flow is decelerated and the turbine does not get enough air to run, and therefore these are two aspects that can in fact slow down the turbine wheel, but this requires very, very costly sensors and actuators, because it has to be achieved in the shortest possible time, because as I said, it's a very, very short interval phenomenon. So therefore you have to be very, very careful while dealing with it. Either you can use reliability data, or you can use test data in order to ensure that the disk does not burst. Now, in order to design the disk against the disk burst, you will have to establish the speed margin. That means even if the turbine overspeeds, it does not burst till the overspeed is to certain extent. Now, how do you choose the burst margins? You can either have the radial burst, or you can have the hoop burst. These are demonstrate rather schematically represented, very, very idealized. That means if the disk is broken circumferentially, then that is the radial burst, and if it is broken along the radius, it is called the hoop burst. Because remember that the stresses perpendicular to the radius are nothing but the hoop stress, and the stresses that exist along the radius are nothing but the radial stress. So the direction of radial burst and the direction of hoop burst are very, very easy to reckon. Now, why the radial burst is not recommended? That is because the radial burst heavily depends on the distribution of the radial stress, how exactly it is distributed, and it increases unsteadily, and then the radial growth increases till the centrifugal forces bring about the failure. So therefore it is the radial stress that is limited. It is not allowed to increase beyond a point, and it is the margin that is decided against the hoop mode. So that is where we choose hoop burst mode. It is not just understanding the failure, what mode of failure that is actually convenient to design against, that is more reliable, that mode has to be chosen to design against. So let's proceed. In fact, in order to design the burst margin, you use a parameter called area weighted hoop stress, and this is very easy to derive, that at each radius where the hoop stress is varying is multiplied by the elemental area, and it is integrated across the disk and divided by the total area, and that would give us area weighted mean hoop stress. And assuming that the disk burst happens at let us say 75% of the UTS. Now here one important aspect I would like to bring, that is the temperature degrades the mechanical properties seriously, and now since the UTS is also affected by temperature, the minimum value of the UTS at that temperature must be assumed, and that would give us the following burst margin. When I say burst margin, you must understand that this is the margin to which the turbine disk can overspeed. And why it is proportional to square of the FOS or factor of safety? That is because the stresses are proportional to square of the speed. Stresses are proportional to square of the speed, and therefore the FOS is root of FOS gives us the speed margin. Now let us look at a few other cases. Now this case is pertaining to manufacture of gears. Now most of these components, let us say gears or bearing track, they have to be heat treated. That means you will have to provide certain depth of carburization. Of course, you can choose whether it is carburization or whether it is nitriding, depending on the various requirements. You can design, rather you can choose the type of heat treatment. Now, the depth of case hardening is very important, because as you travel along the depth, which is very shallow, for example, practically for a gear, the case depth of hardening is around 0.4 to 0.5 mm, right. As we travel along this depth, the hardness which is required, let us say around 64 HRC to begin with on the surface, but as you go deeper, this hardness significantly drops, and it drops parabolically. That is, non-linearly it drops, and therefore the case depth has to be maintained very carefully. Now here, before the gears are sent to heat treatment, the dimensions that we measure are called the green dimensions. If they are not measured properly, let us say the tooth thickness measured before the heat treatment, let us say is L, which is greater than the allowed the tooth thickness. Once it is carburized and ground, once the material is removed, what happens is your actual carburization depth, which is required, let us say around 0.4 to 0.5 mm, would have come down, and this can lead us to failure, because but for this hardness, considering the contact loads and the surface velocities, the gear tooth can be reduced to knife edges in a very short period of time if the hardness is very low. Now, one of the second aspects that you also got to be concerned with is the surface engineering. That is, I am talking here about phosphating. In fact, phosphating gives anti-scuffing property for gears. Therefore, it is very important that where the contact pressures and contact velocities are significant, the gears are phosphated. And this process has to be very carefully done, because if you are considering a carburized gear, which is very reactive in a phosphating bath, you not just have to be worried about the bath pH value, the temperature, and the time of exposure. If you expose the component for a longer period of time, then there is every possibility that the gear might lose dimensions. So we are now looking at one more important facet of design, that is heat treatment and surface engineering. So let's move on. Now here is one more interesting assignment for the students, and again this also can win you some prizes. In fact, for this question we would be giving away a prize of the Fundamentals of Stress and Vibration, authored by my colleague, and this is a very comprehensive book. Now the question is, generally the gas turbine is started by starting the HP spool, because this is the spool with the minimum mass moment of inertia. That means within a very short period of time you can start the engine. In fact, you can assess it with basic equations of motion if you idealize things. But today people are talking about starting this fan which has maximum inertia. You can have a detailed discussion on how it is possible. It can be the variable frequency generator issues, it can be issues regarding the fuel saving, it can be so many other issues. If you could write to us in a detailed way, like why starting a fan, whether it is advantageous, disadvantageous, whether it is possible, whether it is not possible, taking into account all the issues, then the first 10 people would be selected for this particular award. Now I spoke about so many aspects, right? In the beginning I gave the example of bearing support structure, and I emphasized that a single component can have several consequences, right? Because the bearing support structure not only influenced the rotor dynamics, the engine vibrations, it also influenced the tip clearance, and I told you tip clearance is a very important parameter, not just for the compressor and turbine performances. It can also affect the surge margin, that is a very important aerodynamic margin of the compressors. Surge is a phenomenon, in the simplest possible term, it is the ability of the compressor to push the air is lost, and as a consequence instantaneously with a big bang, the flow is discontinued, and the flow also gets reversed, and the combustion can move both forwards and rearwards, a very damaging phenomenon. So therefore a single component, if not designed properly, can affect several of the performance parameters. Then we also looked at unobvious failure mode, the Poisson effect in a bolted joint. We also looked at pattern recognition. We gave the example of discontinuity stresses. We also discussed the disc burst, whether you should choose radial burst or hoop burst. Now, there are so many facets. Is there a learning methodology that would enable you to conceive all such issues and become familiar? Yes, indeed. In fact, myself and my CEO have conceived this powerful methodology which is used for engineering learning. This is called engineering wheel. And let me take you through this particular pedagogy, which is a very important pedagogy. Now, here I have taken a very simple concept of Poisson's ratio, and this is called the Poisson wheel. And look at the number of engineering applications I have listed here. Don't think that these are only the applications. The applications can go any number of times. For example, we learnt this today, right? A rotating bolted joint does suffer loss of clamping load because of the Poisson effect. And this effect is also relevant in structural geology. And this effect can also bring down what is known as mass locking in finite element, because you appreciate from the fundamentals that the bulk modulus is proportional to E by 1 minus mu, and if this particular value of the Poisson ratio goes to 0.5, then the bulk modulus would go to infinity. That means the volumetric response gets locked out because bulk modulus is the one that determines the volumetric response, and that gets blocked out, and as a consequence what happens, the volumetric response is not got, and that is called mass locking. And it can also apply to pressure vessels, it can also apply to composites where you can get a negative Poisson's ratio. It can also be applied to compare beams and plates. So therefore, one concept, that is the Poisson's ratio, is actually linked to several applications. Now, let's consider one more situation. It is not just conceiving the failure modes. How smartly you address these failure modes becomes very, very important in an industry. Now, let's take the example of a pipe which is located close to a static structure. Let's say the pipe is vibrating significantly, and there is an apprehension that it may hit the static structure. If it does, then there is every possibility that the pipe breaks, and it can have consequences depending on whether it is a fuel pipe, whether it is some other pipe. So the consequences either can be grave, or definitely it can be a damaging consequence. Now, if I ask any young enthusiastic analyst, he would say we will have to do harmonic analysis to capture the vibratory response of this particular system. Now, do we have to go down that route, because you may have to understand a lot of parameters. For example, the available damping itself is not known. It is very difficult to quantify that. How would you go about? Here goes a very, very simple method of addressing it. Now, if you say that this pipe is vibrating, then consider it to be a beam with whatever constraints it has. And since we know that the first mode, the first flexural mode, is the most potential mode, then you can in fact apply a force to deflect it. And if the deflection is equal to the clearance between the static structure and the pipe in the equilibrium position, and still this is elastic, then there is every possibility that the pipe in fact ends up hitting the static structure, because it is elastic. But if you deflect the pipe by the equilibrium separation between the pipe and the static structure, say delta, and the pipe has assumed a good amount of plasticity, then obviously the pipe cannot hit the static structure, because once there is plastic deformation, it cannot continue to have that vibratory energy, and therefore the failure is avoided. I mean, this is a very, very simple analysis, right? I mean, you are simply talking about the deflection of the beam due to applied central force, rather than complicating the analysis with harmonic analysis. So therefore it becomes very, very, very important for us to look at all these issues. Now let's move on. Now, as far as this discussion is concerned, we would be looking at now various interviews that were conducted in service industries, OEMs, and research labs. One of the first expectations in these industries is your ability to idealize systems, and therefore you can see that I have posted a simple picture here of a windmill, and the windmill is idealized as a cantilevered beam, since the tower has a substantial mass and the mass is lumped at the end, and then we have estimated the natural frequency of this particular system. It is very simple because 3 EI by L cube is the stiffness of the cantilever, and this divided by the effective mass of the system, that is the mass of the turbine system and the lumped mass of the tower, both are here, and if I substitute the effective mass, I get the natural frequency. This is a rough estimate. It gives a good insight and a feel for numbers as far as this structure is concerned. And this is one of the basic expectations of the industry. Let's find out more. Now, one of the philosophies of industries is that a young designer or an analyst who comes out of the university is expected to have the following. The first trait that I am going to talk about is competency in physics and mathematics. Today, people also expect the candidate to have a good exposure to MATLAB or Python coding skills, because even in mechanical industry, the culture of data analytics has started for several predictions. And knowledge of materials is very, very important. We will have several case studies on this particular thing. And as far as the organic traits go, one needs to have visualization, feel for numbers, and critical thinking. We'd look at various types of visualization, because when I say visualization, it need not be just a spatial or drawing reading. It can be abstract, it can be mechanical, figuring out how a mechanism works or how a flow behaves. And finally, appreciation for engineering failures. That's very, very important. And what we reckon is creativity, that is ability to sketch effective concepts for components and systems, is something that comes from experience, or some may be born with that gift. Though appreciation for manufacture and assembly is indeed a requirement, unless you work in the industries, a perfect visualization, a in-depth understanding is difficult. So we would focus on these four important traits. We start with physics and mathematics. We then go to materials, visualization. Let me cover as many case studies as possible. Now, before we go to the actual industry cases, look at these examples where engineering common sense was put to work. Now, fan is one of the most noise generating member in an engine, and look at this scarfed inlet. The noise generated from the fan comes down, gets reflected at the bottom and goes out, so that the community down below is not affected. Look at this simple example of copper and aluminum wires, because copper wires are far more effective in conducting heat, because their conductivity is almost twice that of the aluminum, and therefore they have a much better fatigue life. But aluminum is lighter and cheaper, copper is costlier. How do you get the best of the both worlds? In the 1960s, people introduced copper clad aluminum wire, the birth of composite material idea, where you get best of the both worlds. So therefore, it is the simple ideas that are expected by the interviewers from the interviewees. So now let's discuss these things. The order of the discussion would be, first we would look at examples for competency definition. That is, we would unravel some of the finest minds. In fact, my CEO interacted with several competency heads and several interviewers. I put my own personal experience and my team, and then we have put together some of the best interview scenarios, be it ISRO, DRDO, Rolls-Royce, Airbus, and then we have collected several of these situations, and we hope you would really enjoy. Let's move on. Now, when I went to one of the interviews, to begin with, though there were detailed technical discussions, one of the questions that I was put was, can you define entropy? Right? Now, I was surprised because I had gleaned into several subjects on the previous night. Being a young engineer, I was very, very anxious, and I had put in a lot of preparations, both physics-wise, mathematics-wise, but I was surprised when I was asked to define entropy. One of the philosophies that industries follow is the philosophy of keep it simple. Why? Because if you are able to put across a concept, that a person who has never had schooling can appreciate, anybody can appreciate that particular concept. Because if you are discussing the issue of bearing support structure in a meeting, you have a person who has been into manufacturing all his life, and when you say that the natural frequency is brought down by flexible bearing support structure, then he may not understand. But if you say that if the shaft is kept on a flexible platform, then it deflects more, it becomes less stiffer, then that idea is immediately bought. So if I give a earnest thermodynamic definition for entropy, people may not understand, and that is where you have to have maximum clarity on your understanding and then put it across in a way that anybody can understand. Now, certain questions can be why Kf in bending is less than Kf in axial, which simply depends on the stress distribution across the cross section. You can also have a question why an IC rotor has torsional frequency 10 times the operating speed, because there can be unseen events which can load the shaft almost 10 times the steady state load. There can be questions which can be very, very difficult to answer, because how exactly a boundary layer behaves when the viscosity goes down, because for no slip condition, it is the viscous forces which actually decelerate, rather become almost equal to the inertial forces, and therefore how the nature retaliates when you are reducing the viscosity. That can be a very, very involved question. And sometimes mathematical equations can be related to physical reality. For example, if somebody is from the CFD domain or fluids domain, or even a mechanical engineer would have pursued fluid mechanics, and if you consider one of the viscosity models, a d-viscosity model, and if you observe carefully, it is very clear that a strain tensor is related to a stress tensor by a scalar. That means you are actually encouraging symmetry. That means you cannot accommodate asymmetry, and that could be the basis for you to develop a new model which addresses asymmetry. So the interviews can be very, very involved, but let's start with a simple one so that we appreciate every facet of it. One of the service industry interviews that I was provided, I don't want to name the company, it is a real-time interview, and those students who are the participants can in fact pick a few leaves on how to answer this particular question. The question is very simple. I think in your curriculum under strength of materials you would have pursued thin cylinders. Now the question is, a thin cylinder which is subjected to pressure, let's assume it to be a metal cylinder, how exactly the radius and the pressure are related? That means, does the ability of the cylinder to support pressure is determined by the curvature of it? Now, the first question that should come to your mind is, how does the ability to support pressure varies with radius or size? If I assume that one of the two geometric parameters, that is thickness and radius, out of which radius of course obviously is variable here, if I assume that the thickness is constant, and then for the above, the relationship for a material and other geometric parameters is needed, and obviously, and in order to establish that relationship between material and geometric, I need to resort to stress limit. Once I say stress limit, the obvious question that arises is what is the dominant stress? There are two stresses. One is the hoop stress and the radial stress, the longitudinal stress. And out of these two stresses, obviously we know that the hoop stress is dominant. That is, it is twice that of the longitudinal stress. Now, therefore, if I am talking about the stress limit, it is the hoop stress that has to be limited, and obviously it is limited by the material strength, because a material can withstand certain amount of stress, and here I am talking about hoop strength. Now, the formula is obvious, PR by T, it can be easily derived, a standard textbook formula, and that is equated to material strength. And now, since I have assumed T to be constant, we now get a relationship that is PR is equal to constant. So that means a smaller pressure vessel, that is a pressure vessel with the curvature higher than a bigger pressure vessel with larger curvature, but a smaller curvature but larger radius cannot support higher pressure. It is the smaller pressure vessel with larger curvature but smaller radius can support higher pressure. And also you would immediately recognize that the nature of the curve resembles several practical situations. For example, the same relationship holds for a clutch with uniform wear, and the curve also resembles the constant strain energy curve. It also resembles the isothermal process curve. These are just incidentals. But the bigger question is how exactly the interviewer conceived this particular situation. So now, if you look at these two structures, that is, one is the plate, another is a doubly curved member, it is obvious that the shells, if you are have had a lesson on plates and shells, you would immediately recognize that the shells are far more structurally efficient. That means if you are looking at supporting certain stress level, a very, very thin doubly curved shell can support against a very, very thick plate. The idea can be incepted from a very, very small situation. If you take a thin wire, it can be bent very easily, right? But if you are trying to subject a thin wire to axial loading, it can rather support a large axial load, but it can be bent very easily. And therefore, a doubly curved shell can support a very, very large amount of load. Now, let's come to the mathematical understanding of it. Here I have assumed a circular plate and I have assumed a shell, and the students who are attending can attempt this calculation on an XLS and carry out a parametric study. And here you can see that the stress experienced by the shell is 76 megapascal, whereas that of the plate is 348. And look at the weight of the shell and look at the weight of the plate. It is 8.5 times that of the weight of the shell. Of course, it is highly idealized, but this would have inspired the interviewer. And why? Because in aircrafts, bulkheads are used where large pressures have to be reacted. Of course, there are exceptions where you require space. You can continue to use a plate which are structurally very, very inefficient. That means we have walked from a very, very basic pressure vessel concept to the concept of bulkhead. That is what in Innovent we call the culture of from concept to technology. So, of course, for the want of time, I haven't detailed. I have just discussed a few elements of it. There are several incidental technological elements that are associated with bulkheads, because they are not just subjected to pressure loads, because they can also be subjected to the torsional loads because of the other structures of the aircraft. So a lot of things to discuss, but one thing we would like to drive home here is that whenever an interviewer, an accomplished interviewer poses a question, at the back of his mind is the technological familiarity that he has, that he wants to understand whether a candidate is able to map his understanding to that. Now let's move on. Now let's look at one OEM situation. Now, how do you decide the HP spool speed? The question is very simple. How do you decide the maximum RPM the HP spool can support? Of course, if you look at some of the latest civil gas turbine engines, the HP spool can go up to 13,500 RPM, a very, very large RPM. And therefore, if you look at a turbine blade, it delivers a power which is almost 700 to 800 horsepower, especially at the time of takeoff, where the engine is put to maximum use. And therefore, the turbine blades become very, very critical, and they have to be analyzed. And let's try and see how centrifugal loading can decide or rather estimate, because there are several factors. We are making an overly idealized estimate. How can you can get somewhere near to the exact RPM. Now, before we make any engineering hand calculation or any answer is presented to the interviewer, what an young engineer must do, he has to be very, very systematic. He has to state all the idealizations. Because if you have looked at, if you can Google it also, a simple blade, if you look at a turbine blade, it can have twist, it can have tapering. Especially turbine blades we will have a shroud on the top. You can simultaneously Google and see, because for the want of clarity, I want you to look at a particular blade. And also you also have to understand what other stresses are there, because here we are trying to estimate the speed based on centrifugal loading. But that alone is not the only loading agency. There can be thermal stresses. Because of the gas flow, there can be significant bending stresses. Of course, the bending stresses definitely will be less than, for example, if the stress due to CF is around 250 MPa, let's say, for instance, the bending stresses could be hardly around 100 MPa. But again, whether these bending stresses must come into picture or can they get cancelled because of some design, let's find out. It's pretty involved. Now, this is the cross section of the typical turbine blade, and you can see that I have also sketched the principal axis. When I say principal axis, in strength of materials, most of the students would have pursued it. That is, axis of minimum area moment of inertia and axis of maximum area moment of inertia, especially for a structure which is not symmetric. For symmetric structures, these axes coincide with the actual geometric axis of symmetry. But since it's an asymmetric section, you have to have two principal axes of inertia. And here this is the x-axis, this is the y-axis, and it is obvious to reckon that x-axis is the axis of minimum area moment of inertia, and this is the maximum area moment of inertia, right? Now, again, those who are from the fluid domain would understand that how a turbine blade develops the torque. It is the movement of momentum of the fluid. As the gas hits the turbine blade, as it flows across it, there is a movement of the momentum of the fluid, which is represented by this particular matrix. These are the three unit directions. Axial, this direction coincides with the engine axis. This is the tangential direction perpendicular to the blade, and of course the radial direction along the blade length. And once we compute this rate of change of angular momentum, we get the torque, which is by Newton's second law. And here there are two torques that are generated. Because of the rate of change of momentum in a direction perpendicular to the blade, that is tangential to it, we get this movement along the axial direction, and it is obvious that bending moment is a vector quantity, that is r cross f, and therefore if you apply force in one direction, it causes movement in the perpendicular direction, and whatever that happens in the axial direction will bring about a torque in the tangential direction. But what is to be remembered is that in the axial direction, it is not just the velocity changes that contribute, but also the pressure changes, right? So now we have understood the typical section of the blade, the inertia axis, principal inertia axis, and what bending moments it is subjected to. Now let's try and understand how exactly these bending moments can be negated or can be avoided. Now, one thing that is obvious, or when we call the engineering judgment, you should be able to assess which bending moment is the dominant one, which can be more, of a rather greater concern. Now, here it is obvious that EMW is the greater bending moment, because the maximum force that is tangential to the blade, that is because these are the forces which drive the turbine and provide the power. And as a simple exercise, my student friends can look at the load path for this particular bending moment, whether it is reacted at the disc root or whether it goes beyond. That has to be investigated. Now, once we understand that this is the moment that is of greater significance, let's see how exactly to mitigate that. Now, if you want to reduce, then EMW must be reduced. And how do you reduce? Because if you split the work amongst the turbine blades, let us say there are 50 turbine blades. Instead, if I make it 55 turbine blades, each turbine blade will have lesser work to support, and as a consequence will feel lesser bending moment. But that is not possible, because if you look at the rim of a turbine disc, let us say this is the fir tree in which the blade is supported. This distance cannot be compromised, because this is perhaps the most loaded area, and therefore the pitch, that is the distance between any two turbine blades, cannot be reduced beyond certain point. Now, what happens to the next point that we may want to consider? That is the cross section of the blade, because we know that if you manipulate the area moment of inertia, if you increase it, the bending stress obviously decreases, because the bending stress is the bending moment by area moment of inertia into y, that is the distance from the neutral axis. So this can be reduced by increasing I, but can I increase the card length, that is the width of the aerofoil? It cannot be, because if you increase beyond certain point, what happens? For example, the flow area exposed increases, the flow is contacting greater area, that means greater frictional losses start coming about. So therefore, in order to limit the friction losses, the width of the turbine blade cannot be increased beyond certain point. So that option also is a limited option. Now, what about the blade height? When you reduce the blade height for a given tangential force, the bending moment cost is F into, let's say, R is actually reduced. But the blade height again cannot be increased, because what could happen is there can be tip loss issues, there can be other issues which you can see here. Now, for example, if the blade, let's say, is this tall, let's say h, and in order to have the same annulus area, you can see here, if I hatch this particular annular area, and compare that with this annular area, it is the same, right? Now I want to reduce the blade height by keeping the same annulus area, because I have to keep the same axial velocity, because for a given mass flow rate, the axial velocity can be kept constant if the area is maintained, right? That means I can have shallow blades, that is smaller blades. You can see smaller blades, but here my blades are larger, but this cannot work because you are making your disc much larger. And as the disc grows, what happens? The centrifugal loading becomes significant, and the disc is the sufferer. So this option also is not possible. And incidentally, note that the natural frequency of blades is proportional to 1 by L cube. So therefore, that criterion also influences the choice of blade height. Now, let's come to the centrifugal stress effect. This is very, very important. Now, apart from causing stress, the centrifugal loading also has other incidental effects. One of them is stress stiffening. That means if you stretch a bar or a beam in the axial direction, then what happens? It becomes so stiff, the beam becomes so stiff that its resistance to lateral deflection increases. And a similar phenomenon happens when the blades are subjected to large centrifugal loading. That is because when the blades are pulled out axially, that is radially, by centrifugal loading, the deflection to the lateral loads becomes smaller, and this phenomenon is called stress stiffening. These, this affects only the lower modes, that is, let us say the flap mode is influenced maximum, which is the most potential mode, because in vibration, every component wants to vibrate in the simplest possible mode, that is apologies, thanks to a bad internet, we lost you. Coming back, now we tried various options of increasing the card length, decreasing the height. Now let's consider how centrifugal effect can be used to minimize the bending stress, and in fact it can be cancelled for certain operating points, and that effect is also called the blade leaning. Now, if the centroids of the blade cross sections can be shifted, then centroid of the blade cross sections are shifted, then the centrifugal load will have one moment about the root, and the gas bending will have exactly opposite moment, and there is every likelihood that these two moments get cancelled. That means if I look at the section of the blade, now since the blade leaning is a very, very important technology, and it again depends on both CF loading and the RPM, because on a hot day the density will go down because of the temperature, and on a cold day the density will be higher, but the speeds can be lower, and on a now therefore it is just one operating point that we could address, and then it would be significantly effective for other operating points. And there are several research papers on blade leaning on the internet, and youngsters who are aspiring to take up design can go through that. And one of the questions that might come to your mind is that why have we chosen the gas turbine? Because it is next to rocket science. Be it materials, be it loads, everything has a challenge, and that really boosts your learning curve. Now I was talking about pattern recognition. Now let's come back because we have one more opportunity for pattern recognition. Look at here. we were talking about the blade stiffening because of the CF loading. Now, the same phenomenon repeats if you are looking at a thin rod at the end of which a heavy mass is attached, and this here, gravity is the stiffening agency. This can also occur in pressurized cylinders. It can also occur in cables and strings which are subjected to tensile loading. So therefore, we looked at discontinuity stress pattern recognition. Here we are looking at stress stiffening. Now, we can make a very basic hand calculation. That's what I said in the beginning. A simple hand calculation can reveal a lot of things. You can see here that considering the blade to be a prismatic member, because we neglected taper, we neglected the twisting of the blade, a prismatic member, I have deduced an expression for the centrifugal stress, and that is expressed in terms of the annulus area, because I said annulus area becomes a very important parameter, and of course that in turn limits the amount of centrifugal load that you can apply if the material stress is limited. Now, once we have got the stress in terms of angular velocity and annulus area, what we can do is find out or estimate the angular velocity, and as I said, the maximum root stress could be certain percentage of the minimum operating UTS. Let me again stress on the point that because of the temperature, the UTS is brought down, and the minimum UTS must be used, and that gives us the estimate for the operating speed. Now the question is, can we apply the same to the compressor? Because once you establish a fact, is the fact relevant in some other situation? Yes, indeed. If you are trying to consider the same for compressor blades, it is not significant because the compressor blades are running cooler, and they also don't have shrouds, which significantly contributes to the centrifugal loading, because shrouds are generally at the top of which is used only in case of turbine for higher efficiency, because losses have to be avoided. Look at here, the shrouds are used. Shrouds have several duties to perform. In fact, they provide frictional damping, and also they provide they add to the centrifugal loading, and sometimes they can also reduce the vibrations. But one of the trickier things that you will have to know is that how do you locate the CG of this, because it is contributing to the centrifugal loading, but it should not end up contributing to the bending loading also. So you must ensure that the CG of the shroud is closest to the axis of minimum area moment of inertia, because we want to contribute to the minimum bending moment about the minimum axis of inertia, because we know that the bending moment by the area moment of inertia is the one that causes bending stress. If the bending moment is along x-axis, then the inertia of that about that axis has to be considered. So therefore, we want the shroud CG to be located very close to the axis of minimum area moment of inertia, so that it does not contribute to significant bending. Now, this is the reason I have been saying that if one turbine blade is lost, it can be extremely penalizing for an engine than a compressor blade, because the turbine is power generating, so therefore it can have a huge amount of camber. When I say camber, it is essentially the total deflection of the flow, incoming and outgoing, and that means that you can extract maximum power in one single stage of the turbine, but you can provide very little power in one stage of compressor. And that reminds me of one of the famous principles of fluid mechanics, which says that it is always easy to accelerate a flow than to decelerate. Now let's look at one of the interesting hand calculations. In the beginning, several loads are very important. When I was discussing a bearing support structure, you might remember that I spoke about these maneuvers, pitching and yawing of the aircraft, which can bring about a huge amount of gyro loading. And of course, we also spoke about inertial loading and thrust loading. Now, one of the loads that you want to consider and one of the loads that we want to consider here is the centrifugal load. When I was young, working for the gas turbine industry, and most of the youngsters who are participating can actually research this. Here, you can in fact carry out a sensitivity analysis between efficiency of a turbine stage with respect to the relative tip clearance. When I say relative tip clearance, it is the tip clearance divided by the height of the turbine blade. It's a very important thing. Why the Thomas and Alfred, of course, they independently proved that non-uniform clearance causes rotor whirling. That is because when the tip clearance increases, the tangential force developed at that location decreases, and when the tip clearance increases, the force increases, and a net force is developed that would cause the whirl. Of course, I don't get into the aerodynamic stiffness and other aspects for the want of time, but you can research this particular topic, a very interesting topic, where both between the limits 0 to 2 pi and minus pi to pi, you can see that the area. Now, I sincerely apologize for the bad internet in between. But to summarize, what is very important is the physics maths culture, and which must be mapped in its entirety to every facet of the product design. And that is the way to learn design in the Innovance experience. And I would like to thank each and every participant for his or her time. I hope in this short discussion you have picked up a few leaves. In case you want further webinars, we would be happy to help you on the topics that we discussed today at length. It can be fatigue, it can be random vibration fatigue, or any other topic that you are interested in. We would try and have a more specific webinar where your learning curve could be more consolidated. And also, we will be looking forward to those questions that we posed during the webinar. I hope you would be excited to win those prizes. And once again, on behalf of my team and myself, thank you very much. We are looking forward to your feedback, which is very important for us to improve upon. Thanks to certain internet constraints, this webinar did have a few disturbances, but I think next time we would look at those issues in detail. So please write to us, and these are the email addresses. Please make a note of these addresses. Please write to us. All your queries would be answered. The questions would be collected, segregated and answered, and those answers would be posted on our website. And for a limited version of the presentation material, please visit our LMS. And once again, thank you so much, and I would like to see you next time soon. Thank you so much.